So we are live. Good morning, dear Henry and all of North America. Good afternoon, dear project partners and all of Europe. Welcome to our second webinar for the Erasmus Plus project 3D STEAM with the title Accelerating STEAM-related Knowledge and Skills via 3D Modeling and 3D Printing. Our speaker today is Henry Segerman, a mathematician working mainly in three-dimensional geometry and topology, and a mathematical maker and artist working primarily in 3D printing. He is a professor in the Department of Mathematics at Oklahoma State University and the author of the book Visualizing Mathematics with 3D Printing. Let's welcome Henry with his presentations entitled Learning by Doing with 3D Printing and Variants of the 15 Puzzle and the Effects of Holonomy.
Well, thank you for the introduction. So I have two talks, which are, I guess, aimed at sort of different groups. So the first talk, the first slide is on screen at the moment, is really about my experiences in teaching a course which is primarily based around 3D printing. It's a mathematics course. We'll get more into that in the next few minutes. And then the second talk is really more using 3D printing to illustrate non-trivial mathematical ideas in a way that would be very difficult to do in some other medium. So it's more sort of like applications of 3D printing outside of pedagogy. And I should mention, I have a package which is apparently going to be delivered today. They say it will be after the end of this talk, but there's a chance that I might have to jump up and answer the door to sign for my package. So I apologize if that happens. Okay, so let's start with the first talk, learning by doing with 3D printing. So I got into I got into 3D printing probably 15 years ago or so. But then I, started seriously thinking about using it in the classroom, in the mathematics classroom in particular, maybe 8 or 9 years ago, something like that. And so it's worth thinking. And again, primarily, I'm thinking in the mathematics setting, but more generally, what are the ways in which 3D printing can be used in the classroom? And so the first, which I think is the easiest sort of approach, is that the teacher is going to bring 3D printed objects to share with the class. So manipulative visualizations, ways to help students understand what's going on. And this is sort of, it doesn't sort of disrupt the course in other ways. You're just bringing it in for a class to look at a particular thing, and then they go away again. But the one that I focus more on, which is well, disruptive maybe isn't quite the right word, but the course is really going to have to change if the students themselves are going to be designing and 3D printing things. And that's the course that I've worked with. And so, yeah, I mean, the questions that I needed to ask, or that anybody wanting to do something similar would need to ask. How much of the course is going to involve 3D printing rather than whatever other content is supposed to be covered in the course. And so, yeah, so you could either, I've heard of people using 3D printing as an add-on project on top of, for example, a calculus class. You might have a group project, which is, not about calculus, but about 3D printing with calculus. That would be an add-on project to an existing course. And then the route that I have gone in the course that I teach is to build the entire course around 3D printing. And so this would be not so easy to fit into a standard curriculum. You would need to, have a new course, which, I mean, you've got to argue within whatever university system you're in to make this work. And then, yeah, I mean, another question: where does the 3D printing happen? And again, there are a couple of options here. So there are lots and lots of 3D printing services. When I first started out in 3D printing myself, not in an educational context, for many years I would just send off files to a 3D printing service, and they would send it back to me. I didn't own my own 3D printer. And that works, although there's some costs, but it's high quality. You get very nice results. But then the other option, which is the one that my course uses, is that, well, we have our own 3D printers in a 3D printing lab in the mathematics department, or there are lots and lots of maker spaces around. And then the big advantage there is the faster turnaround. If you're sending things off to some company, then maybe it takes a week or two at the least. And if your students need feedback on what's happening, everything sort of slows down. So I mean, 3D printers are not lightning fast objects, but it's better to, for them to be able to iterate over, they can get a print done in an hour or so, then that's better. So this is a shot of the 3D printing lab that we have here in the mathematics department at Oklahoma State. And so, yeah, I mean, I had a lot of support from my institution to say, okay, yeah, we're going to get funding for a 3D printing lab. And more importantly than that is to have the space available. Space is always a problem in academic departments and so on. But we have a dedicated space that the students have access to, and that they can, go and print their projects at, 11 p.m. on the night before the homework is due and whatever. Okay, so you might ask, why is it advantageous to have the students learn to do the 3D printing themselves? So my course is it's a mathematics course, and 3D printing is maybe more usually maybe to learn it in an engineering or an architecture course, but we're getting mathematicians to learn how to do it. And I think there are a lot of advantages to having them actually do it themselves. So at first, it's very motivating. So the students, they get to take home something that they made with their mind, right? And particularly in mathematics, less so in something like engineering, that's unusual, right? In mathematics, usually what you end up doing is taking exams, and that's the sort of thing that you produce as to show that you knew what was going on in the course. And here it's something very physical, and again, that's much more motivating than I did a homework or I did an exam. In terms of like selling such a course to a university, to a department, so this is, wants to be a sort of project-based course rather than specifically looking at, looking at specific skills that you want to learn, like a course in linear algebra or calculus. I think it's more valuable to have a course that sort of consolidates all of the skills that the students have learned in past courses, and then they get to actually apply them to real world problems. And again, this is something that I think engineering students will have more experience with through courses that they generally have. 3D printing is really good for project work, and it's difficult, I think, to do. I mean, there are ways to do projects in mathematics. So, for example, I mean, you can do pure mathematics research projects where you come up, the teacher comes up with problems which the students have to work on, or maybe you have some more applied setting where the idea is that a business has some problem that they want to solve, and the students are trying to work on this. But if you're doing 3D printing, then it's sort of, I think, easier to get the students to be motivated by a problem that they themselves are interested in. Like you can have a problem that's a student that's maybe interested in, some sort of hobby or something that they do on their own that then can feed into a project much more easily than if it's just sort of a written output. And this is something that I was hoping would happen, and maybe I don't know if it did as well as I hoped it would be. With 3D printing, the students hopefully will self-correct the errors that they make. So a lot of times in a homework or an exam setting, they figure something out and they get an answer, and is it correct or not? Who knows, right? They don't necessarily have the skills to evaluate their own work and be sure that it's correct. But if they're then interacting with the 3D print or with the 3D design software or the 3D printers, if their calculation is wrong, then something will go wrong. Often, right? The thing that they've made is not the correct size. It's not doing the right thing, and hopefully they have another visual backup to notice that there's a problem. So I think there's lots of reasons why these things are exciting and relevant for students in mathematics and other STEM subjects. And again, yeah, 3D technology is likely to be very relevant. It's something that they can take forward to their future careers. So I have a few shots of examples. These are all US based. I understand there are people doing things in Europe, but I don't have examples to hand. But so here's one of the projects that I heard about. So Laura Tallman is at James Madison University, and she had I think these are generally sort of one-off courses that people have run rather than sort of repeating courses. But this was a sort of knot theory / 3D printing course where students learned about knot theory and then learned how to 3D print illustrations sort of showing the different aspects. So there's, all these standard sort of knot pictures, and then this is a surface whose boundary is a knot, and there's various other, this is a sort of stick number of a knot. There's various kind of aspects of knot theory that you can illustrate with 3D printing. Chris Hanusa is at Queens College in New York City, and he has a course, and you can see this is, the technology is sort of different here. This is using, there's some metal 3D printing, there's some color 3D printing. I think this was using a service where you send off your files and then they come back, rather than the sort of having 3D printers in a lab somewhere. And yeah, so, and there are a few others, but this is, these are some shots from my course at Oklahoma State University. So the course is called Geometry and Algorithms in Three-Dimensional Modeling. And I guess I'll mention some of the, I guess what I'm going to do next is just sort of go through, like, how does the course work? How do we build the skills of the students up to be able to get to this work? And I'll get to the different sort of projects later on. These are some of the results from the first sort of major project that the students do. And the idea here is that the students need to produce a goblet, a glass, a drinking vessel that holds a precise amount of volume, so 100 milliliters. And the idea is that, students have learned various ways to, for example, using surfaces of revolution, they can calculate the volume of those surfaces of revolution with some integration techniques from Calculus 2. And so this is sort of, applying that. But of course, they don't have to do surfaces of revolution. If they want to do something else that has some interesting mathematics, like calculate the volume of a dodecahedron, then they can do that. So yeah, I'm going to go through, I think that the most important part of making this work is really the homework. So the homeworks, well, so I have there is some lecture component to the course. We start sort of alternating between lecture classes and more hands-on learning how to use the software and the 3D printers and so on. And in lecture, I'm, talking some about the background of what the computers are doing in order to work in 3D design. So I talk about transformations of space, and I talk about how to, how does the computer talk about curves, so Bezier curves, this kind of thing. But the sort of hands-on things and the homework is, well, the homework is split between, do a couple of questions from the book. That's more along the sort of lecture part of the course. But then the other side, I think, is the more important for getting students building their skills of how to work with the software. And so I'm going to talk about those parts of the homework. So, and the students come in, without the prerequisites that I give are to multivariable calculus, because I want them to know about parametric curves and surfaces and so on. And I want them to know about vectors, and also linear algebra, because I want them to know about matrices, because they're going to be using matrices to transform things. And maybe there's a prerequisite that they should have seen some sort of programming, but there's a large range of expertise in programming. And most often the students have not seen the software that I'm using, which is Rhinoceros. And so the first homework is just get used to the controls, right? How do I move the camera around? How do I make objects? Not worrying about the 3D printing yet. And so yeah, the first homework is to just design a cool castle, right? Because people have all sorts of ideas about the kinds of things that they want from their castles. They want to be able to do, cuboid shapes and maybe cones for the spires of your wizard's tower and things like arches. So this is getting into Boolean operations between different objects, and these are all things that I want them to learn. How do I make things? Although again, this is not this is how do I make a picture on screen. It's not yet 3D printing. And then the second homework is the sort of first 3D printing one, where I really carefully step them through. How do you design a keyring ornament? So well, there's more stuff here that I don't expect you to read all of it, but here are your initials, and then you can thicken them up using precisely this tool, and then you can put them together and do a Boolean union operation to merge them, make sure that there's a hole for your keyring, change it from a NURBS object into a mesh object, and then you can 3D print them, and very step by step. Here are all of the things that you would need to do in order to get the 3D printer to do the right thing. And here are some of the key rings that the students, apparently this was from 2023, that they produced. And so and there's a secret second there's a secret second thing that I'm getting the students to do. I'm not telling them, here's the text tool, you should make your letters using the text tool that's in Rhinoceros. I want them to draw them themselves, and I'm asking them to use these sort of Bezier curve objects so that they're used to them when they see them later on. Right, and the advantages of doing a keyring in this sort of design, the probability of 3D printing issues are low, because they shouldn't have any overhangs in their design, right? Everything is mostly flat. It goes, you print a few layers up. You don't need scaffolding. It's just a simpler 3D print to do. And then the third homework here, we're really sort of getting into more of the mathematics. So the homework here is find some interesting parametric curve, either from your previous classes, or you find something interesting on the internet, and then 3D print it and make a design from it. And so you're seeing all of these sort of spirals and torus knot kind of shapes and things like this. And so I supply them with scripts that they can modify, and really almost everything is done for them in terms of the programming part. They just need to substitute in their choice of curve that they want to make. Although, and this is already sort of getting into one of the hopes for the course, and when it works the best, this is the kind of thing that happens, is that the students get excited and they want to do some complicated curve that's so the functions that go into the definition of this curve are not standard functions. They're not your standard programming mathematics library. They're not sines and cosines and exponentials. They need to do something else. And so then now they have to, they've learned how to do Taylor series somewhere. And now they have to actually do it. And they have to, come up with a way to use the programming to approximate this curve that they want to make. And maybe I'll tell a story about, the best outcome of this is that they run into interesting problems in the application of these abstract ideas that they've learned in a calculus class, but then they really run into issues that they have to solve. So I had a student who, again, was working with some curve that required the use of a Taylor series to define, because you couldn't build it out of sines and cosines and so on. And they were having a problem that it was some sort of spiral that at some point would just sort of shoot off to the side. And they were very confused about what was happening. And what was happening is that they were running up against floating point precision issues, that they have some number of terms in the Taylor series approximation, and they're reaching the limits of what the floating point numbers can represent. And so we needed to really get into some details of how to mess with the underlying mathematics in a way that if you're just a mathematics student and you just say, okay, the calculator just tells me the answer, you wouldn't have access to, you wouldn't be having those experiences. The fourth homework is, you've done parametric curves. Now let's do parametric surfaces. And again, really the same sort of thing, but now we're working with surfaces. And again, they find interesting surfaces and they build something from it. And again, I supply them with the software or the programs to modify to do what they want to do. So the course is a project-based course. So now they've done sort of 4 homeworks. They know how to 3D print things. They know how to 3D print surfaces, which are parameterized. And now here's the first project. And I guess I mentioned before, the goblet project, which should hold a precise amount of water. And again, students get really excited and they want to do interesting things, and they want to do things which are not just surfaces of revolution. So, so I guess this is a pipe, right? This is from sort of like a Mario game pipe or something like this. So I guess this is a surface of revolution, but then you have to add these on here. But then something like this horn really is a more complicated integral. And so, yeah, when the students are getting excited, the strongest students can really run with it and decide, I want to do something more complicated and really get into these thornier issues. Whereas maybe the not so strong students, they can do a standard surface of revolution, but then they can add something in terms of decoration. Whenever they're doing these kind of things, they're designing some sort of fancy shape. I'm always encouraging them to think about it in a mathematical way. And it sort of, it inevitably comes up that there's mathematics in the design of, even if it's as simple as like, how is the symmetry going to work for these different thorns around this cup? So the mathematics sort of naturally comes up, but there's a wide variety of projects that students can do. And it is a project-based course. There's a couple of take-home midterms, but then the main aspects are 3D printed projects. That there's 3 main projects throughout the semester. The 5th homework, now we're back on the homework schedule, is about transformations. And so again, they've learned about using matrices to transform objects, and now they get to apply it. And this is sort of just iterated transformations. So they know about 4x4 matrices as used for transforming objects. And then, they can just this is just a repeating sequence of these things. And here the students are already learning about support and how to make sure how to deal with overhangs. And, here this is some sort of more complicated combination of a bunch of different things. And this is getting a little bit more into the programming because they've got to deal with for loops in order to be able to do this kind of thing. So the second project, usually I'll show you a little later. Usually it's a sort of a programming-based project, but there was an interesting opportunity that we had in 2023 for a sort of joint project for the whole class. So what happened then is that the Museum of Art here at Oklahoma State University were planning a show on geometry and math. And this was in the fall, October, December of 2023, and the course was running in the spring. And so the idea was that as a whole, the students would print out the different counties of the state of Oklahoma. So each student would have 5 or 6 different counties, and the idea was that they would design something to fit on that county that would say something about the history of Oklahoma or some interesting feature there, and so on. And so I had to actually I did a lot of work in coming up with getting sort of accurate topographic information for the state, and then cutting it up into pieces and then giving the students access to those pieces. And also the ability to put things in precise positions. So how do you match up GPS coordinates with the coordinates of the 3D prints? So that was a fun project, and an interesting way to sort of have everybody print their objects and have them fit together into a unified whole at the end. The 6th homework, so I think the first 5 homeworks that I mentioned, these are really getting the students up to speed on the basic objects. But once they're there, they can sort of do whatever, right? They know how to make curves and surfaces in pretty much whatever shape they want. If they have a parameterization for it, they know how to do repeated transformations. And so now I think that the last few are just a really kind of inspiration almost for future, what do they want to do with their final project, or just other interesting things that you can do. So the sixth homework project, at least as it is at the moment, is sort of about light and projections. And so there's two kind of uh, ways that I'm hoping that they'll do something. So one is the stereographic projection shadow idea, which I guess I was the first to come up with, or the first to implement. But then there are also these sort of objects that you shine a light through in different directions, and you get different behavior. And so the students generally have come up with some nice examples of this, and they learn how this works and so on. And again, we're now deep into projects where I just want them to do something interesting and learn how to do something. So this is sort of making puzzles by dissection. So how do you fit these objects in here, or here's some shape and then you cut it along planes or helices or helicoids or whatever it might be to make a puzzle. And here they're getting a little into a little more into the engineering issues of things that move, right? You have to have a little bit of a gap between parts. If you print them so that they fit together perfectly, you won't actually be able to put them together. There's too much friction, and so there's a little few things like that. I don't have a specific homework which gets into, say, mechanisms, although I know so Sabeta Matsumoto at Georgia Tech teaches or has taught a 3D printing course which is more aimed at graduate students and scientists. The idea being that they can use their 3D printing skills to make things they need for their science experiments. They need some setup for whatever kind of experiment it is, and they're learning these skills to be able to 3D print those things that they need. And she gets into mechanisms and hinges and all kinds of interesting things. So these are the so as I mentioned, the map of Oklahoma project was a sort of a special event that we did for the second project. The usual one is just a programming project, and sort of I want to force. There are some students who are very familiar with programming and it comes easily to them, and there are some that haven't done any for 3 years, and so I want them to have some sort of experience with that. And so the second project is specifically do something involving programming. And but there's a lot of freedom, right? So they can do a 3D design and animation, some sort of interactive demonstration even. So Rhino Python or Grasshopper. Grasshopper is the 3D, is the parametric programming language within Rhinoceros. And I give them a few ideas of things to do, but usually they go off and find something that's a little bit different, or they can do their own thing entirely. So parameterized curves in space, but can you make it more of a project than it was as a homework? Graphs. So a lot of things with fractals. So fractals work very well with iterating transformations. So L systems are sort of related to that, or Nautilus shells, pine cones. So Fibonacci sequence, the spirals to do with pine cones and so on. And then the final project is really just wide open. I want them to do something mathematical and illustrate it in some way. And again, by the time they've got to this point, they've seen a lot of different things, and they usually come up with some interesting idea, which is really their own, and they own it. So I'm going to show a few examples of projects from students. So again, this is the kind of fractal tree idea, again, growing out of for loops to do transformations. This is sort of more looking at polyhedral geometry. How do you come up with the geometry of the icosahedron and so on? This is the kind of pinecone geometry, and this one is more. This is a Menger sponge, which again another kind of fractal. Fractals can be quite difficult because you have to they're very complicated geometrically, when you represent them in a 3D software. And so there can be some sort of does your computer blow up issues with doing these kinds of things. This was a fun project where the student made these kind of 3D printed rollers, so for putting patterns into your cookie dough. And so this is dealing with symmetries and wrapping a design around a cylinder and so on. Here are some other ones. This is so here. I mean, you can see that they're getting into it, right? They wanted to paint it as well. They didn't just want a 3D printed object. They wanted it to look beautiful, and so they printed it. This is a tree based on L systems, some sort of parametric surface mesh thing. This was an interesting project where the students. Well, so what are they illustrating? They're illustrating. I forget which of Kepler's laws it is. There's one of Kepler's laws is the with an elliptical orbit of a planet around the sun, the time that is spent going from around one part of the orbit is equal to the area. I think that's correct. Right? It's equal area in equal time. And so this is, it's a sort of a bathtub idea with which you can fill with water, and the water tells you can empty it out and put it into the other one to show that it's the same. It's the same volume. It's the same area. And the mathematical difficulty is that there's no nice parameter. I mean, it's an ellipse, but there's no nice parameterization for the ellipse that moves at the correct speed. And so the student was already deep into wanting to do this project before they realized how hard it was going to be. And then, of course, that's the idea, right? They're forced to sort of learn all of this other stuff to get the result that they want. This was a nice illustration of Fourier series. So we start at the top with just the straight line here, and then as you move further down, we're interpolating between different numbers of terms in the Fourier series for the sawtooth wave or the square wave on the right. This is a similar sort of thing with some sort of Weierstrass function, which is continuous but nowhere differentiable. Oh yeah, so during the pandemic, we didn't actually do much in the way of 3D printing. In fact, any 3D printing, because we didn't want people to come into campus. And so instead, all of the things that people produced were animations and things like this. And so this was one of the final projects there, where the students sort of recreated the strand beast mechanism and animated it and had this walking dog as their final project. It's very impressive. And then I think maybe this was from 2024. This was a student who wanted to recreate the Hoberman sphere, the expanding and contracting sphere. So, I mean, a few issues that have come up. Having to do this, I mean, to do something like this, it has to be a course on its own. This is not, you couldn't fit the amount of time that I spend having the students learn how to work with the 3D software. You couldn't do that in a standard calculus course or something like that. It just wouldn't work. So this has to be its own course. The prerequisites that I have are quite high, requiring that they know multivariable calculus and linear algebra. I mean, there are plenty of students, the mathematicians and engineers primarily, but it is quite restrictive. This isn't an experience that you can give to people just coming into the university without that background. In order to do this, I mean, so like Chris Hanuza's course in New York, so he's having the students design things and then send them off, but it's much easier for the students if they can iterate it. So you need space for your own 3D printing lab in order to do that, or maker spaces. There are many universities that have maker spaces these days. And I mean, one of the big issues is that I, as the teacher, need to have a lot of expertise in 3D design in order to help the students with their problems. So I'm going to be actually on sabbatical in Paris in the spring of 2026, and this course usually runs in the spring, and it just won't run because no other faculty member would be able to do it. because they need the mathematical background to know what the issues are, but they also need all of this, software background and 3D printing expertise. And so it isn't sort of easily transferable. I mean, so if you want to set this up yourself, you need to have some experience with this. Otherwise, the students, I suspect, will be sort of lost. They run into problems and you don't know how to solve it. What are they supposed to do? And I guess the last couple of things that I'll show in this first talk. So this was Kyle Van Deventer was a student an undergraduate student at Oklahoma State. He took my course in his third year, and then in his fourth year, he did a senior project with me. He was he did mathematics and aerospace engineering, so he wanted to do something that was mechanical and also had some mathematics to it. And so this was the project that we came up with these kind of expanding, twisting kind of self-similar scissor linkages. Yeah, this was, this was a very exciting project, and I think, really worked well. And again, it's unfortunate that the prerequisites are sort of high, which means that most students taking the course are in their final year. But in this case, Kyle was able to work with me afterwards on a project in the year. And this is just a quote from George Hart, another mathematical artist. The more math you know, the more stuff you can make, which absolutely true. And that's sort of something of a moral for this course. Okay, so that's the first talk. I don't know if we should maybe pause and see if there's any questions on this first talk, or maybe I'll just move on to the second talk. What do you think?
So far, there are no questions in the chat. So
okay, let's move on then.
yeah.
And let's see. So I'm going to switch over to my other talk if I can find it. Here we go. Okay, so whoops. Okay, so this is a talk again, not so much on the kind of education side, but more on the what can we do with 3D printing to do interesting things. And I guess this is somewhat sort of research focused, but I think it's more the idea. I would think of this as sort of a how do you make complicated mathematical ideas accessible to the general public? And so this is about well, it will end up being about holonomy, which I will explain as we get there. So this is the 15 puzzle. I expect that almost everybody has seen this before. I mean, this is sort of the precursor of the Rubik's Cube in a way. It was a big craze around 1900 or so, late 1800s. You slide the blocks around, and then you have to get them back in the correct order. And one of the popularizers of the 15 puzzle was a guy called Sam Lloyd. And he sort of had this challenge, which I think made it really sort of go viral in the way that virality was over 100 years ago. He had this classic conundrum, which was, can you get or show how to get from the usual order 1 through 15 like this to this order where the 15 and the 14 have been swapped? And he offered a prize of $1,000 in the 1890s to anybody who could show how to do this, how to swap the 15 and the 14. And the money was safe because it had been proved 10 years earlier that this is impossible, that there is no way to swap just the 15 and the 14. Maybe I can just briefly explain or give a hint of why it's impossible to do this. So this is a permutation puzzle. When you're sliding tiles around, what you're doing is you've got these sort of 16 spots, and then there are, you can think of it as 16 tiles where one of the tiles is the empty space. And so what you're doing every time you do a move is you're permuting 2 of the tiles, and then you see what kind of configurations you can get to. And so here's the argument that says that you can never just swap 14 and 15. So think about what has to happen. So the empty tile starts in the bottom right, and then you move it around via some complicated path, and then it gets back to the bottom left. But however you move it, whatever you do, you must, whenever you go up, eventually you have to come back down. So there are as many up moves as there are down moves, and there are as many left moves as there are right moves in order to get the tile back in the bottom right corner. And so the number of moves has to be even. And it turns out, so there's a result in group theory, that any sort of permutation that you have, it has a parity. It knows if it's an odd thing or an even thing, and an odd thing can only be made with an odd number of swaps, and an even thing can only be made with an even number of swaps. And the move that swaps 14 and 15 uses one move which is odd. And so you can never get there with an odd number of moves, but in order to get the empty square back in the bottom right corner, you have to make an even number of moves, and so it's impossible. So, how can we cheat Sam out of his money somehow? This is the first design that I came up with to do this. So what have I done here? So I've taken the 15 puzzle and I've wrapped it around a cylinder. So here you can see 1, 2, 1, the start of it, 1, 2, 3, 4, wrapping around 5, 6, and so on. And here, this is the empty tile, the 16th tile, which is now next to 1. So I've wrapped it around to add an extra connection of the tiles. And what does that do? So if I play this video, so here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's in the standard usual orientation. 1, 2, 3, 4, 5, 6. I make 7 moves. And that 7th move uses that extra connection. And since 7 is odd, that breaks the argument from before. And so then I'm just doing the usual sort of, how do you solve the 15 puzzle to try to get this to work? And here we are again, back to the start, except it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 14. So you can swap the order. If you have this one extra connection, that means that you make an odd number of transpositions to get back to the start position, and that's all you need. You use it once, and then you just solve it the same way. So that's one way to change the puzzle to make it work better. Here's another variant where I've changed things. So this looks like the ordinary puzzle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, but you can see that there's something going on here. So if I show from this side what's going on, I've jammed in an extra 4 tiles. So I call this a 15 plus 4 puzzle. And so there are 4 extra tiles that have been jammed in here, and I've put hinges on the edges of these sort of 2x2 blocks. And when the hinge is flat, you can slide a tile across from one spot to the next. So what does this do for you? Well, it introduces an odd length path again. So, if I go from here around to here, and I have to bend the frame in order to make the moves that go around, but this is an odd length path. It's a length 5 path. And so maybe you think I can do the same trick. Since I've got a path that's an odd length, I should be able to swap 14 and 15. But there's something else that happens at the same time, which I want to point out. So the 11 tile is the same way up as the 10 tile. If I slid the 11 in place of the 10, they would be the same way up. The same with 10 and 6, and 6 and 7, and 7 with 16. But 16 and 11 are not the same way up. So this is the effect of holonomy. When you go around a closed loop, but in a surface that somehow has some curvature. So this corner here where I have 5 90-degree angles meeting, at that corner that has some curvature, negative curvature as it happens, and that means that when you go around it, you get rotated. And so with this puzzle, when you solve it, not only do you need to get the numbers in the correct positions, but they also need to have the correct orientation. And so that changes the answer for, is there an impossible configuration or not? So it turns out the mathematics of this has been worked out. Kind of surprisingly, maybe back in 1997, people were thinking about this kind of thing when there were no, as far as I'm aware, no physical puzzles that did this. But they have a result here about sliding piece puzzles with oriented tiles. And here, somewhere in this mess of a theorem, is the answer to the question that you might ask with this version of the 15 puzzle with orientation. Is there a configuration that's impossible to get to or not? It turns out that there is. You can get all of the tiles in the correct positions, but to get the orientations correct as well, you need to there's some things that you cannot do. Well, so after doing the 15 plus 4 puzzle with one vertex that had 5 tiles around it, I decided, well, why stop there? Let's have every vertex have five tiles around it. This starts to become much less a puzzle that you would want to physically play with and more of an art piece, because it really gets quite fiddly. But you can maybe appreciate or imagine what it would be like to work with this. Maybe there's one thing I'll mention here about the numbering. So with the 15 puzzle, you have the numbers in rows. With this 15 plus 4 puzzle, let me, I guess, go back a couple of steps. With the 15 plus 4 puzzle, I kept the same sort of strategy, and then this, it's just sort of an extra thing, and I put it in, and the rows here match with the rows here, but not here. But once you get to every vertex having 5 vertices, the rows and columns don't really make sense anymore. So instead, the numbering sort of goes in a spiral. So maybe you can see there's a 1 here, which it's got a sort of arrow that's pointing at the 2, which points at the 3, which points at the 4, which points at the 5, and this kind of spirals outwards, 7, 8, 9, 10. And again, this is just some sort of way of seeing that you're in the correct position. And I guess I should also mention there's a sort of sub puzzle that comes up with this design. Whenever you want to make a move and slide a tile from one square of the frame to another one, you need the frame to be flat in order that it can slide across. And there can be some restrictions from the rest of the pattern of these hinged squares that you cannot necessarily bend a hinge flat without doing a bunch of work first. So whenever you want to bend the frame, you have to bend along a line that spans across the entire length of the puzzle. And so you have to sort of work on parts of the puzzle elsewhere in order to eventually get into the position where you can actually bend across the entire puzzle. So I haven't really thought about this more deeply, but there's some interesting mathematics, I think, in positions of this shape, or you can imagine anything which is just Euclidean squares arranged hinged with 5 around each vertex. What are the possible configurations of that in space? Can you get to every position? I believe the answer is no. Even for a simpler version of this, you cannot get to every position by just bending it. There are some things that you need to sort of do. Excuse me. There are some positions that are inaccessible by continuously bending things. So anyway, there's some interesting questions there. If you don't want to think about the bending, if you just want to play with the puzzle, here's a version which was people may be familiar with. There's a game called Hyper Rogue, which is a roguelike game based on the hyperbolic plane. And so the people that designed this are researchers at University of Warsaw in Poland, and they used their hyperbolic software to make a interactive version of this puzzle that you can play at the link there. This doesn't have the bending issues, but it does show you what it is like to play with this puzzle and to mess up the orientations, and again dealing with the holonomy that happens when you send a tile around one of these vertices. It gets rotated, and so that makes it more difficult, of course. So let me move on to a different kind of puzzle that involves holonomy. So this is kind of more of a disassembly puzzle. We've got this purple sphere, and then there's this green piece that's in the sphere. We call this piece a rook, as in the chess piece. So in chess, the rook travels along straight lines and then can turn 90 degrees. And that's also happening for this piece here, except that it's on a sphere. And we have a 90-degree triangle. So again, this is the geometry of the sphere means that triangles can have 3 90-degree angles, and that still works. And there's a different effect of holonomy here. So here the rook, this piece is in its sort of home, its arm is in that little holder, and then it goes around this triangle and it comes back, and it no longer fits into its home because it's been rotated. And again, this is the effect of holonomy, that you go around a closed loop on a curved surface and you come back rotated. There's some design going on here. You can see in the channels maybe there are these rails that are happening here. And the point of those is to stop the rook from rotating in place. Obviously, we want the person playing with the puzzle to have to use holonomy to rotate the rook. You don't want to be able to rotate it just in place. So when you get to the exit, so the way to get the rook out is to get it into the correct orientation relative to this sort of home position, and then you can just take it out. And so the puzzle is, how do I get it out? And of course, there are these pegs here, which make it more difficult for you to get it out. This is this sort of a cross-section view showing how the foot of the rook travels along these channels with the rails and stops it from rotating in place. This is sort of an interesting little problem in how do I constrain the shape so that it fits inside of, so that it cannot rotate in place, even though you can move it in different directions. And then, as I say, right, there are these pegs to prevent. So the arms of the rook bang into the pegs and stop it from moving along certain paths. And so this is really a maze where the maze depends on the orientation of the piece as well as just its position. So there are 6 positions you can be at around the sphere, and there are 4 orientations that the rook can be at for each of those positions. And so there are a total of 24 places you can be in this maze, which is a pretty small maze, but nevertheless, it's quite confusing because you sort of cannot see all of the maze at once. There's an interesting way to think about orientations of an object. So take a sphere of radius pi, and you imagine your objects in the middle of the sphere, and then as you move through the sphere along a line from the center, you rotate the object around the line that you're moving along by the angle, which is the distance that you've moved. And what this does is it maps all possible orientations of the object to this ball of radius pi. And in this ball, opposite sides get glued to each other, because if I rotate the object by 180 degrees or pi in one direction, and I rotate by 180 degrees in the opposite direction, I end up with the same orientation. So what this is telling you is that the set of orientations of an object, it matches up with this 3-dimensional space, which is a ball with opposite points of the ball identified, glued together. So mathematically, this is a space called the real projective space, or RP3. And so what I've drawn in here are the edges here are ways in which the rook can move when I'm rotating from one position to another, but I'm not allowing you to twist in place. So you can see here, this one up here and this one down there, those are rotated by 90 degrees, but that's a rotation in place, which I'm not allowing because I want people to use holonomy. And so I've knocked them out. And so we have this sort of network of edges. That's how that's how the rook can move if there are no pegs in the way. This is a sculpture that Chaim Goodman Strauss made, showing that same network, but sort of physically. And so the challenge is to put pegs in a place which remove some of these edges, in fact, pairs of edges, in order to make an interesting puzzle. And so that was the sort of challenge of how to put the pegs down to restrict the movement of the rook to make an interesting maze. And here are a few different puzzles that I came up with. These are all generated by the computer, so I need to do a computer search to find mazes that have a good distance from the start to the end. You have to sort of go around and do complicated things. And in order to, this slide is maybe the most technical here. It's really just how to talk, how to tell a computer how to deal with this problem of what does the maze look like. And so you can use so I talked about these positions in RP3, these orientations. You can use quaternions in order to record those objects, and then we can use quaternions for each node of the graph where you can be in the maze. There's a pair of quaternions for each edge of the graph, connecting those together, and you can also use a quaternion for each peg position. And then it's a matter of like saying which pegs do what to the maze, and there's a nice sort of way in which the quaternions for the peg positions interact with the quaternions for the nodes of the graph and the edge. And so this lets us sort of algorithmically test possible what happens when I put pegs down in particular places and so on. And so this is the kind of graph that I generated for what the maze looked like. So a couple of different examples that I generated. And here are a couple of puzzles. Again, if you put the pegs in different places, you can get very different feeling mazes, and you get different interesting variants. Here's a version on a dodecahedron instead of an octahedron. So this obviously makes things more complicated. Same sort of idea, but there are many more places you can be, and there are more orientations you can be as well. This is the geometry of how the foot of the rook travels through. Again, you want to restrict it so that it can never rotate in place. These rails that get in the way. There's an interesting thing that happens here with the holonomy. Of course, there's holonomy again, but here maybe you see, so here's this rook. It goes around a pentagon and it gets rotated by a sixth of a turn. So there's sort of an interesting thing to ponder. Why is it that I go around a five-sided thing, but I get turned by a sixth of a turn? What does the 5 have to do with the 6? And the answer is something to do with the Gauss-Bonnet theorem, but maybe I'll leave that to questions if people are interested. This is the geometry of the exit. So again, that has to be designed specially so that there's a thing to stop the rook from getting out if it's not in the correct position. This was another sculpture that Chaim Goodman-Strauss and us made of the network. So it's a more complicated network of positions that the rook can be in. Here's us making it. So this is me. This was during the pandemic. Apparently, I stopped cutting my hair. This is Speta Matsumoto, this is Chaim over here. Speta is doing a very important thing of telling us what to do, while Chaim and I do all of the actual physical work of putting it together. Oh yes, and so the computer search here was sort of an interesting question. So it's the same sort of thing. Where do I want to put the pegs to make for an interesting maze? But there are a lot more places to put pegs. So there are 30 edges on a dodecahedron, and you can put a peg on either side of an edge. So that's 60 possible positions for a peg, and the peg can be either there or not. So that's 2 to the power 60 different possible mazes, which is too big to search on a computer in a reasonable amount of time. So we have some sort of pruning techniques. So first of all, if you've got a peg here, you shouldn't have one on the opposite side, because then you're just sort of making this edge impassable, and that sort of seems uninteresting. But we also had some other, we also ruled out some other ones which produced some sort of configurations that tended to produce dead ends. So if you have this one and this one, then it means that there's sort of, it turns out that there's more opportunities for dead ends, which are kind of aesthetically less pleasing to play with than somehow it's more fun to wander around a maze and get back to where you started than wander into a dead end and have to backtrack. Somehow it's more interesting or it's less frustrating to do it that way. And here are some graphs that we came up with. And here's, because everything's done on computer, I can get the computer to solve the puzzle for me, so I don't have to figure out how to do it. And here are some of the designs. These ones in white have no pegs. So I made these. If you just want to illustrate holonomy and you don't want to worry about solving a maze, then there's these versions which are just for illustrating, and the peg versions to make it into a puzzle. Okay, so that was positive curvature on the sphere. What about negative curvature? You can play the same game. Here was a rook inside of a genus 2 surface with right-angled pentagons. And again, when you rotate or when you move the rook around one of these pentagonal faces, it gets rotated. It turns out it gets rotated in the opposite direction from when it was a sphere. Actually, very recently, Edmund Harris and I have worked on this idea of using these sort of holonomy illustrations in sort of an exhibition format. So these, let's see, do I have a better picture? Yes, I do. So these are three, we call them holonomy blocks. These were very recently exhibited at the Museum of Mathematics in New York City. And this is really just showing like, well, so this is the rook is now a sort of metal thing. We had a pointer on the top in the final version, which would show you as you go around the loop that it gets rotated. Of course, in the flat one, it doesn't get rotated, and this sort of negatively curved pentagon, it does get rotated again. And right, here's sort of a video showing sort of the idea. So Edmund Harris is at University of Arkansas, and he's an expert in CNC wood carving, so computer controlled wood carving. And so this sort of combination of the two, right, you can see all of these holes that we drilled in here. So these are to register the 3D printed parts, these sort of lips on the top to keep the rook in. So registering the 3D printed parts with the carved wood parts. So this is a really fun project, and we're going to show it, I think, I think it's going to be in the, or at least we're applying for it to be at the ICM, the International Congress of Mathematicians, which I think is in Philadelphia in 2026. Oh, and here it is at the exhibition at the Museum of Mathematics in New York City. So this was an exhibition with lots of things to do with curvature and surfaces and so on. There's another photograph. Okay, couple other things I want to show you, and then I'll quit. So this is a puzzle, sort of going back to the 15 puzzle, which in the sense that you have tiles that slide around and you mix them up and then you have to get them right back to the correct position again. I call this the continental drift puzzle. So you take out this tile in the South Pacific and then you slide the continents around, hence the name continental drift, and you mess up the planet and then you have to get everything back into the correct position again. And yeah, so this is, again, like the 15 puzzle, except that it has holonomy now. So you need to get the pieces back into the correct positions, but also with the correct orientation. I guess last thing that I'll show is how do you take this to really three-dimensional things? So this is a mass-produced puzzle called Rubik's Slide, I think. And so maybe you can see here there are these cubes have 6 colors, one on each side, and you slide them around the edges of a larger cube. And so this was the sort of, oops, let me go back. So this was the sort of CAD concept for a version of this that would involve holonomy, where when you slide a cube along an edge, it gets rotated by 90 degrees. And again, there's sort of some complicated stuff to do with what happens at a corner. You need the cube to be able to get into the corner and get out in 3 different directions, but it's not allowed to rotate in place, which is sort of difficult. And here's the sort of physical object. Again, I think this falls more into the artwork rather than puzzle you'd actually want to play with, because again, it's quite tricky to work with, but it was a fun challenge to do. Okay, that's my second talk. So thanks for your attention.
Thank you very much for presenting your work. It's a very fantastic, amazing things you are doing here.
Thank you.
So, as I told you in the beginning, probably there won't be any questions
That's
except
okay.
maybe here in WebEx from project partners. On YouTube, we have been followed by many people, but yeah, they were cheering you. It's really cool and so on, but there weren't any questions. So
Okay, great.
if there is no question here in WebEx, then I think we can terminate this this webinar. Thanks again, Henry, for being here and show us everything you have done. It was really amazing, and we will try to stay in touch.
Great, thank you.
So streaming has been stopped.
Okay,
We can
great.
talk again.
Good.